That's good. Who's recording? Okay, so you have oh, Richard. So while Richard is helping, let's just start. Okay, so for this part, so by the way, so if you click this, the code, right? You have two options. One is hide all code, the other is show all code. If you click on that, so here, for example, if you go to this case study number 1, it actually shows you all the necessary R code, right, to reproduce the analysis. So obviously, I know not everyone here knows R, so I guess my current plan is that I will go through all the lecture content. And at the very end, if time permits, I will let you to have a hands-on experience to try to, manipulate those R codes. And while at the same time, if you have any questions, me and Richard will help you. Okay. Okay, so maybe let me first of all hide all code, right, to focus on the content here. And here we will have 2 case studies. So if you click on these 2 tabs, so this is the first case study where you can access the full story by clicking this link. And here is another case study. And so I'm not going into the detail here, but later on we will have some of the parts of these 2 case studies to illustrate the concept. Okay, so now let's go to the first part of today's workshop, which is the scientific process. So the first topic is typically, okay, how people actually get to have their research question, right? So basically what they have, I mean, obviously this is one way, right, for people to generate their research question is to based on the observation or based on their prior knowledge. So here, for example, the case study number 1, there's a 1 sentence which was copied from the original paper. So here, there's one medication which is efavirenz. Correct me if I pronounce it incorrectly. So the observation to this medication is that this efavirenz-based combination may not HIV infected individuals. Okay, so based on this observation, then one of the natural research questions from this observation was that, okay, in this case, what if we don't contain, right, we let the medication which don't contain this particular virus, how would that compare, right, with medication has that in terms of the long-term efficacy and the tolerability, right? So this is sort of like one example that how people generate their research question. And for example, for the second case study, well, this is some modified content. So the observation is that adherence to antiviral medication is vital. So this is sort of like people's understanding, right, about this adherence, about this fact. And then one natural question generated from this observation is that is there a difference in HIV control between those who adhere to their medications, right, versus those who do not, right? So naturally, they stratify those people into 2 groups, right? One adhere, one do not. And then we want to see whether there's any difference in terms of HIV control. Okay, so this is, first of all, you have to start with the research question. Otherwise, you don't really know how you are going to collect data, right? The data is obviously, you want to have the most informative data that's related to your research question. Okay, so so now we have a research question, but also, right, remember, you are going to collect data. So you have to think about a link between the data versus your research questions, right? And this is related with the primary outcome, right? So how you are going to use the data to represent the most important questions you are interested, right? And so that is the research question must be stated in terms of the primary outcome. So for example, if you are saying, well, I'm going to compare two treatments, for example, treatment A versus treatment B. And your hypothesis would be that treatment A is much better than treatment B, right? So in this case, this research statement would be very vague, right? So because you can ask, okay, so A is better than B in terms of what, right? So you have to state these research questions related with the primary outcome in terms of, for example, safety or in terms of much longer survival rate, etc., right? So this is an example of the primary outcome. And obviously, you can define different, the primary outcome, types of primary outcomes. But in terms of like if you want to conduct quantitative analysis, the primary outcomes has to specify some specific characteristics. Okay. So first of all, it has to be measurable, right? You have to be able to quantify this primary outcome so that later you can conduct any analysis. And well, in terms of biostatistics, right? So this primary outcome has to be clinically meaningful, and also it should be of the greatest importance. So, for example, you in one study you could have multiple outcomes, right? So the most important one is called primary outcome. So, what do you think? What we call the second one? Yes, yes, that's good. Yeah, the secondary outcome, etc. Right? But people, I mean, mostly focusing on the primary, right? And then there are some follow-up analysis to talk about to analyze the secondary, etc. And well, most of the cases, right, you are going to conduct statistical hypothesis testing to compare, but this is going to be a later component of this workshop. Okay, so now we talk about you are going to determine, right, how to measure the primary outcome so that make your research question quantitative, right? And now it comes to how you are going to design scheme to actually collect data. So this is actually the way, the part where we actually need to use statistics, right? So have you, do you know, like, what's the difference between the population versus sample? Anyone knows? Have you heard of population? Yes.
The population is the entire group and a sample is a subset of that group that's represented.
Yes, that's good. So, well, obviously, right, if you can afford to take a measurement of all the entire population, that would be the best, right? Because there's no error, right? You can just accurately understand what this population looks like, right? But obviously, in reality, we know that we have many constraints, we have lots of difficulties, right? We cannot afford to make the measurement of the entire population, right? So here, this dark blue circle represents the entire population. And typically, when we perform statistical analysis, we are trying to make analysis on the part of the population, right? And later on, right, we want to use the knowledge we obtained from this part, like small part of this population, to make inference, right? Basically, we want to generalize the finding from the small, like, number of this sample, right, to infer how this entire population looks like, right? So this is a goal of performing statistical analysis, or in our case, the biostatistical analysis, right? So I guess the difference between statistics and biostatistics is that the biostatistics is more focusing on the biomedical related questions, right? Yeah. So here you are going to, first of all, collect data, right? And then you want to do statistical inference, right, to assess, first of all, what the sample looks like, and then linking the sample to the entire population. Yeah, so here is the examples of population, right? As mentioned, that it's sort of like the entire people, right, or the entire unit within a specified criteria, right? So I have a question, right? So suppose I'm interested in the height, for example, for people attending this workshop, okay? So do you think this is a sample or population? Can you say that again?
Population, because this is a whole workshop we're talking about, so that becomes a population.
Yes, right. So this is a population, right? So for example, if I'm lazy, I just say I'm going to just take measurements on 10 of them. So that 10 people will be a sample out of the entire, like, people attending the workshop. Yes. Okay. So this is the population, and then we are going to here, and then we are going to talk about, okay, how can I collect the data, right? How can I do the sampling from the entire population? For example, like what my examples before, right? If I just want to take 10 people, the measurement from 10 people, right? Can you think of a way for me, like telling me that how can I choose which 10 people I'm going to take the measurement?
Draw names out of a hat.
Yes, right, that would be the random sampling, right? But on the other hand, there may be another way. So for example, for me, the easiest way would be I just take the 10 people who are nearest to me, right? But can you imagine what would be the problem of that?
Be biased.
Yes, right. That could be biased, right? Obviously, in this case, you can't say why bias, right? But there are, for example, when you try to take a sample from a population, maybe systematically you tend to take measurements from younger people because younger people are more responding, etc. Right? Then if you do that, then that's a bias. So your results will be biased towards younger people, right? So meaning that your conclusions from the sample is not generating enough to the older people, right? So that's why the sampling, how to take sample from the population is also a very important concept, right? So the idea is that you want to make sure that your sample is sort of like representative to the population as much as possible, right? Okay. So obviously there are at least two types, right? One is sort of like a random sample, one is sort of a systematic sample. But here, different samples, right? Different data collection scheme will result in different types of sort of like study types, right? So here, one is like experiment study versus observational studies, right? So what's the experiment study? So the name suggests, right, you will want to do some experiments yourself, right, on some participants or some units, right? And what's the advantage? Can you think of the advantage of performing experiment study? Yes.
It's very controlled, so it's easier to see any differences that what you're influencing is going to have.
Yes, exactly. That's the best part of doing experiments, right? And the other is observational study, meaning that you don't do any experiment, you don't do any interventions, right? You just record the data, right? So can you think about one advantage of performing observational study?
You don't have to do anything.
Yes. Yes, you don't have to do anything, and what else? Yes.
You've limited your like influence over the data, like any changes that you would have caused. Depending on the subject, also sometimes you can experiment with them, sometimes you can.
Yes, this is like part of the issue, right? When you do like clinical related research, right? You cannot control, for example, you are studying a patient, right? You cannot tell them, okay, force them to not take the treatment or take the treatment, right? There are like ethical issues, right? So sometimes you have to do the observational studies. Yes. Okay. So here, these are the two questions. So for the case study number one, there's a statement about their study. So if you read these sentences, can you tell me whether the study is observational or experimental? So here, the one highlighted, and maybe I just unhighlight. And the Why is that?
They were controlling like how the medicine is being used.
Yes, they are randomly assign 1:1:1 ratio, right? So to randomly assign treatment to they do and they make some intervention, right, to the people. Okay, so how about case study number 2? So after you read it, can you tell me whether it's experimental or observational? Why is that?
They used secondary data was like a study that they designed themselves.
Yeah, so basically they just gave a criteria, right? What's the sort of like the people they are interested, and then they just take numbers, right? They don't do any experiment intervention on them. Okay. So now you learn these two terminologies. Okay, so there was a timing of the study. So basically, there were 2 different types, which is called prospective and retrospective. So, for example, so let's first of all to look at this the definition. So, for the prospective, meaning that the study is designed to collect data in the future, right? I'm going to start a study and trying to collect data in the future. And the retrospective is that the things is already happened, right? You just collect data and backwards. So, okay, so my question is that for the experimental studies, do you think it's typically retrospective or prospective?
Prospective.
Why is that?
Because you're designing it ahead of time.
Yes, right. So typically, right, I mean, not typically, right? Most of the time, right? I mean, all the time, the experimental studies prospective. And so that's why you see the terms of prospective and retrospective that apply to observational studies, right? Because observational study, of course, right? You can design study, but you don't do any intervention, then you can have a prospective studies, right? Observational studies as well. So this is timing is only different timings is only applied to observational studies. Okay. And the measurement, right? So obviously there it involves, do you measure, for example, the patient one time, or do you measure them multiple times, right? And which is longitudinal, right? And also spatial, that is, instead of measuring, for example, the patient from one hospital, you want to measure people across different hospitals. That's spatial, right? Different locations. Okay, and then you can have a single observation, right? You just want to collect data at this single time point, right? So this is at least there were 3 different, well, measuring time and also measuring different locations, right? But remember, this is also important in the sense that for the follow-up analysis, right? For example, if the data is collected longitudinally, that is follows across different time points, right? Then the statistical analysis can be much more complicated, right? Because obviously, for example, people's age, right, will always increase, right? So there's a high correlation, right, across different time points. And also spatially, right? So within one hospital, maybe the people will be more alike, maybe because they are getting treated by like a doctor, like of the same, like maybe same doctor or similar doctors, right? Versus across hospitals, right? So there are like correlations across spatial as well as across time that when you do the statistical analysis, you have to take into account. You cannot simply treat, okay, the observations taken across time on the same people will be independent. That's not a proper way to do the analysis. Okay, so the last part is whenever you're involved in a study, there's a blinding issue, right? So there were at least, I mean, there's a single blinded, double blinded, and triple blinded. Meaning that single blinded is meaning that in a study, participants, they don't know what group they are assigned to, right? So it's a blind towards the participants. And then there's a double blinded. So double blinded meaning that both the participants and the people involved in designing these studies, they don't know like who belongs to which group. And the triple blinded means it's more stringent. It means that besides the participants and the people involved in the study and the people who do the analysis don't even know which group the patient belongs to. So can you tell me why do we need to have this blindness in the study? Is this necessary? Why it's necessary?
So there's a placebo effect, and if doctors, like, if you don't do double-blinded, then sometimes doctors will feel bad for the patient and then preferentially give them treatment, and therefore it doesn't end up being random.
Yes. Just making sure the study or as well as analysis to be more objective, right? Yeah. Don't want to introduce any unnecessary bias, right? Because it's already taking a lot of time, a lot of money to conduct those studies, right? You don't want to introduce any unnecessary bias. Okay, so here from the first article. So here is this one sentence describing their study. So we talk about this experimental study, and then it says it's open label trial. Can you guess what this means? Well, probably you know, right?
Not blinded.
Oh, you didn't know. Can you guess what this means?
So is it not blinded?
Right, it's not blinded, yes. So open label meaning both people, like participants and the people who involved in the design of the trial knows like which groups they belong to.
I have a question. Like in the case of triple blinded study, like how is the analysis performed? Like if you don't know which group is what, how do you compare?
Yeah, this is a good question. So meaning that, I mean, whenever you do the hypothesis testing, right? So you know they belong to the different groups, right? But you don't know which group it is, right? So you still can do hypothesis study, just you don't know this group belongs to the treatment or this group belongs to placebo.
You have like another outside person who's not involved in the study who blinds on the sample for everybody.
Okay, so the common types of biomedical studies. So there were probably you heard of like cohort study, case control study, cross-sectional studies, and under the experimental studies, there were clinical trials, right? This is the most famous type of studies. And so let's go to the cohort study. So the cohort study meaning that exposure-based sampling. So you have a cohort. What cohort means that it's a group of people that fall into a certain criteria. And so here, for example, from the paragraph of the case study number 2, right, it has a longitudinal cohort of 1,092 HIV infected patients, right? What's the criteria of that is it has to be HIV infected, right? And then they have to follow in a wellness clinic in Balabala, South Africa. And it's from this year, 2005 to 2009. So this is the criteria. So make sure you have to define specify a criteria so that you can correctly or accurately define the cohort you are interested, right? And the cohort study, meaning that you will have 2 cohorts, right? One cohort is obviously you want to have a random sample of the individuals that's being exposed to a risk factor or some characteristics, basically. And there's another cohort of individuals that actually do not get exposed to a particular risk factor. So the idea is that you want to compare between those cohorts. Obviously, you're going to follow that and to see their outcome. For example, whether they get infected by a certain or HIV or not, right? And then you want to compare this cohort to see whether, for example, this particular risk factor, right, the exposed cohort by a factor is a important indicator that's linking to, for example, the development of HIV, for example, right? So another one is case control study. Well, the case control study, meaning that it's outcome-based sampling, in the sense that from this name, right, the explanation outcome-based study, meaning that you have to have the outcome first, right? So that means this is retrospective or prospective. Yes, because you already know the outcome, right? That means it's already happened, right? You are just collecting data. So the case control study, as you mentioned, is that often a retrospective observational study. Again, right, you will have 2 cohorts, right? And in this case, one cohort is called cases, and the other cohort is called controls, right? So the cases meaning that a people, right, a subset of the people from that population who meet certain criteria, meaning that, for example, who get HIV infected, right? And the control is that another subset of the sample from the population that do not meet the criteria, which means, for example, they are HIV negative, right? And at the same time, we want to make sure that these controls, right, this control cohort will be as much similar as the cases cohort in other scenarios. For example, in other characteristics, for example, they are similar in terms of age, right, in terms of BMI, etc., right? So why do we want to do that?
We want to reduce compounding factors as much as possible.
Yes, right. So because I don't want to, for example, introduce some systematic bias. For example, one cohort, right, it's all young people, the other is it's all older people, right? Maybe the age will be the factor influencing the outcome, right? But not the specific risk factor I'm interested to study. Yes. And then there's a cross-sectional study. Again, it's an observational study that only measure at one time point. So for example, I just want to take a measurement of everybody's height today, right? So this is taking the measurement at one time point, right? But what if, I mean, maybe height is not more appropriate, maybe the weight, right? I want to take everyone's weight, right? For example, because we have 6 parts, right? Maybe I can take everybody's weight at 6 time intervals, right? Then what does this call? Yes, right. This is longitudinal. I have taken a measurement at each week, right? Each Thursday to see whether, while by learning statistics, whether you are going to lose weight or gain weight, right? Okay. But obviously, if I'm just deciding to take everyone's weight at the very beginning, that's it. Then this is just a one-time point, right? The cross-sectional study. Okay. Yeah. So now the experimental studies, obviously the most important is the clinical trials, right? It involves either the humans or the animals, right? And to study the safety and efficacy of a new treatment. And they can be randomized or not. If it's randomized, then the participants are assigned to at least, right, 2 study groups, right, or different arms. And obviously, again, right, because we assign participants into different groups, right, for example, different treatment regions, right, then obviously we want to match those participants across the other attributes, right, the characteristics. Typically, right, when we conduct clinical trials, we are going to collect data multiple times, right, for example, before treatment and after treatment, right, at least 2 time points to make a comparison. So again, there's another trial called the pragmatic trial. Have everyone heard of this pragmatic trial? No. I mean, I guess, yeah. This is also my first time to actually try to understand what's pragmatic trial. So according to my understanding, the pragmatic trials is similar to the clinical trials. But remember, the clinical trials has actually a very stringent inclusion to the participants, right? You have to have lots of criteria. So typically, the sample size is small, and also the people, and also, right, if you have those stringent criteria, sometimes you will get good results, suggesting the treatment is more effective, right? But in reality, right, because in the real world, obviously, there were lots of other factors, right, confounding factors to influence the results. So people find that even though sometimes the clinical trial suggests the treatment is more effective, but then in reality, people actually don't see that. So that's why they have these pragmatic trials, meaning that it's clinical trial, but it's less stringent than the criteria defined in the clinical trial. So for example, in terms of, for example, the doctors, right, to perform the treatment in the clinical trial, the doctors would be who is familiar with this type of research, right, who is doing the research and also see the patient to perform this treatment. But for example, in the pragmatic trials, they can let other clinicians, doctors who is not like doing this type of research, right, who don't maybe have too much experience in this, and then to see the patients and to give the treatment. So it's more mimicking the real world scenario. So that's why the major difference between clinical and the pragmatic trials. And obviously, you have the maybe many of you are familiar with this lab experiments, right? It's more controllable because you yourself, you can just control, right? The experiment. But obviously, the drawback is that you can only have a small sample size, right, to study. And then there's randomized design studies. Basically, any studies that has to this randomization scheme, right, into that. So it's a very broad. And for the time being, I'm just skip that, right, just to tell you, okay, high levelly there were at least these four different types of important studies associated with clinical biostats, so biological related questions. Did I go too fast? No, okay, good. Okay, so here is just comparing the advantages of you do experiment and you do observational, and we talk about that, right? What's the advantage of what's the disadvantage? So I guess the most important advantage of the experimental, I mean, when you do experiments, right, you can control, sort of like eliminate as many confounding factors as possible, right? So at the end, it's sort of like the gold standard, right, to get some causal relationship between the factor you are interested in versus the outcome. But observational study, right, it's sort of like hard to do that. Okay, so for the last thing is how do we do the random sample, right? So we talk about you can just randomly select, right? This is called a simple random sample. That is, each unit, right, has from the population has the same probability of being selected. And then there's another two commonly used sampling scheme. So one is called a stratified random sample. That means we are going to partition the population into different strata. And within all the strata, a simple random sample is taken. So one example is that I can partition the population I'm interested in according to their age, right? So I will have maybe just, for example, two strata, right? The male and the female. And I'm going to do simple random sample within a male stratum, right? And select maybe 10% of the people here and do another simple random sample from the female group and select maybe 10%, right? And I combine, this is my sample from the entire population. And then there's another type of sampling, which is called a cluster sampling. Again, if you look at definition, they are quite similar, right? Again, the population is partitioned into clusters. And but the difference, the cluster, you can think of these clusters as the similar concept to the strata, right? But you see the difference is how we are going to take the random sampling scheme. Before is that we are going to take a subset of the people from each stratum, right? But here, once we partition the population into clusters, so what we are going to do is that we are going to only randomly sample a subset of the clusters. So for example, if I am going to partition the population into 10 clusters, right? I'm just going to do a simple random sample. For example, I'm going to pick 4 clusters out of these 10. And then for those 4 clusters I selected, everyone belong to those 4 clusters will be selected, will become my sample, the final sample. So that's the difference. So can you think about like in which scenarios the stratified random sampling is more preferred than cluster sampling and vice versa, given the definitions to them and the differences between these two? Obviously, the similarities are they always partition, both of them partition the population into, I would say, different groups, right? It's just how they perform the random sample is different. right? The stratified random sample is that for each of this group, I'm going to subsample a subset of the people from each group, right? But then the cluster sampling is that given the group, I'm just going to randomly select several groups, right? And then everyone belong to those selected groups will become my sample. Okay. Can you think about different scenarios while one is preferred than the other? Right? Otherwise, why do we need to have these two different sampling schemes, right?
Maybe, I mean, if you're doing it by like sex and you want to have an even number of each, if you would sample randomly between each group, you would have the same number in each group.
Yes, that's one. Yes, right. Yeah. Anything else?
I mean, if the population number is high, then maybe you can do for stratified.
If we have a larger size of population, and you are saying we can do the stratified is preferred than the population. The population size is high. So you are saying we can do stratified, meaning that for each group, you can just select a few number of people from each group. But my argument can be, well, for cluster sampling, right? So for example, even though the population size is high, right? I get to have lots of clusters, right? But maybe I can just pick one cluster out of like so many clusters, right? From that question, from your answer, can you infer like in which situation I will prefer? Yeah. I mean, this is a good example, right? Suppose you have a very high the population size, right? And you obviously you can't afford to measure such many samples, right? And as you said, in which case I want to subsample different groups. And in this case, for example, in gene case, I just want to sample one cluster out of the other. But the goal is that, remember, the goal is that I want my sample to represent the whole population. Right? Think about in which case, if I only randomly select one cluster, this cluster will be representative to the whole population. Right? Can you think about a scenario? Well, I can do that.
How do you define the class?
Yeah. Okay. So obviously, yeah, this is a good question. How can we define the cluster? Obviously, the cluster has to be defined according to some criteria, right? Obviously, in this case, right, I can also define my cluster to be according to the gender, right? One group will be all female, the other group will be all male, right? But obviously, that's sort of like this is. But obviously, there are other ways you can define the clusters. Yeah, this is also a good question, right? So if I define how to define the cluster according to the gender, then the cluster sampling is obviously not a good idea, right? Because otherwise, I have two clusters, I just randomly select one, then the Y will always be like one gender type, right? Yeah, this is a good question. So this also talk about the different ways to define the groups, right? Obviously, the stratified random sample can make the population into like distinct groups, right? But then the cluster samples could be, the clusters, right? They are sort of like, well, obviously the people within the cluster are more similar, right? But obviously when you do clustering, the people between the cluster are less similar, right? So that means when we do clustering sampling, right? So I guess the more preferred scenario is that if we know ahead of time that the entire population is more similar, it's more homogeneous, right? So it doesn't matter which cluster I draw or which subset of cluster I draw, then the people will sort of like mimic the real like population, right? And on the other hand, the stratified random sample is more preferred when we know that the population is heterogeneous, right? Yeah. Okay, so this is sort of like everything I want to teach about the scientific process, right? We start with a question and we think about, okay, which are the schemes we can use to collect data, right? Obviously we want to, first of all, quantify the research question by a primary outcome, right? And focusing on the primary outcome, we are going to design, okay, what type of study, right, we want to conduct in order to collect data, and hopefully later on we can use the collect data to answer the original questions we're interested, right? Okay, so do you have any questions? Okay. Okay, so there are exercise. So what do you think? Do you want to do the exercise by yourself at home, or you want to do the exercise here? Maybe let's just do one exercise here. Okay, probably you want to, open the lecture notes at home. Okay, so maybe can you take maybe just 1 minute to read this whole paragraph? Just read it, right? And don't like look at the code, right? Because the code will reveal the answer, and you just want to see whether you understand the concept, right? Okay, so what's the research question for the Duke study?
Is there association between amount of time and the
Yes, right. So this is actually their research questions, right? They want to determine if there is any association between the amount of time since the participants last routine physical and they perceive the trust in healthcare providers. Okay, so what's the primary outcome of the Duke study? So the primary outcome is associated with the research question, right? So basically from this research question, can you think about identify which is the primary outcome? Oh yeah, so basically there are two variables, right? The time, the amount of time since participants last routine physical and their perceived trust in health provider, right? So here the primary outcome is the time since the last physical, right? Because sort of like the trust, right, will influence the outcome, right? If you have a high trust, right? So the amount of time may be shorter or longer, right? So is this Duke study prospective or retrospective?
Retrospective.
Yes. Why?
The data.
Yeah, it's already there, right? The data. You are now collecting the data. Yes, retrospective. Okay, maybe let's just do quickly go through everything. Okay, so question 2, if you can take a quick look at this paragraph. So first of all, is this observational or experimental study? Yes, because it conducted a clinical trial, right? What's their research question?
Will you supplements of potassium?
Yeah. Yes, so the objective here. Okay, so is this a prospective or retrospective study? Yes. Huh? Retrospective, prospective, right? Okay, because you are collecting. Okay, so now what's the population they are interested in studying?
African Americans over 30-year-olds.
And what else?
And have pre-diabetes.
What? Yes, had and what else?
And age.
Age greater than 30, right? And also, right, they have to from Duke, right? The participating in this particular clinics, right, but not every other places. If we don't include this criteria, right, what will be the result? The problem here?
We need to find the worldwide population of that group.
You will have spatial issue, right? They will have everywhere. You will have locations, right? They may have, if they are closer, they may have a high correlation versus they are far away, right? Yes. What's the primary outcome of the study? Yes, glucose metabolism. Yes. Okay, so last one. So first of all, is this a prospective or retrospective study? Yes. And what kind of study is it? Is it outcome-based, exposure-based, or not? What outcome? Yeah. It's outcome-based. Right? What's the outcome? Death? They are all dead, right?
Yeah.
So what's the outcome?
The cause of death?
Yes. What's the cause of death?
Well, it was this, and then there were controls that weren't.
Yes, right. Okay, so now describe the population. I mean, including the population would be including the samples from both cases and controls, right? Combining them, what's the population we are interested in? Yes, the seed infant as well as none, right? Because the population has to include both cohorts. So basically, the infant, right, died under 1 year of age, right? And what else? So this is one characteristic of population. What else?
San Diego.
Yes, in San Diego. And what else? Yes, so this is determining the sort of the population, right? Narrow down the population. Yes. And the primary outcome we talk about, right? The seed. Okay. So let's go to the second topic. So I plan to just talk maybe part of the second topic, and then we will have a break, and then we will get back. Okay. And so now, right, once we conducted the data collection scheme, right, so now imagine that you have all the data yourself, right? So now let's sort of like try to understand what are different types of data. How can we, first of all, summarize the data, right, using some common summary statistics. Okay. So there were at least two different high level, two different type of data, which is categorical and quantitative. Okay, so among this categorical data, there were three different types. One is binary, meaning that it's yes or no, right? 0, 1. For example, the gender, male, female. So obviously, you have to, whenever you code this, right, you have to specify what 1 means, right? Otherwise, if you only code 0, 1, then nobody knows, right, which level the 0 or 1 represents to. And there's another called a nominal in the sense that it's categorical, right? For example, you have different type of treatment, right? But then there's no like natural ordering, right? Treatment A, treatment B, treatment C. It's not necessarily A is smaller than B, smaller than C, right? You can switch, right? C, B, A, or etc. So the order doesn't carry any meaningful, I guess, interpretation, right? So this is called a nominal. Because different type of, even though they are categorical, but different type of categorical variables will require different analysis schemes later on, right? So it's also important to recognize what, even though they are categorical, but what type of categorical variables they are. And the last one is ordinal in the sense that there is actually a natural ordering, right? So because if you take a survey, right, or if you do some questions, it will have like not at all sure, somewhat sure. So you know, right? Naturally, you know there's a natural ordering from this left to the right. So here, there's a caution, right? Obviously, in any data recording, right, there's always some missing values, right? So people sometimes will use a very large, extremely large number to represent a missing value, right? But this obviously doesn't carry any information, right? It's just to indicate this is a missing value. So again, this is categorical, right? You cannot treat this 999 as numerical values. Okay, so among the quantitative, right, there are at least two types, right? Discrete, that is, it's countable, right? When you sort of like integers, right? 0, 1, 2, 3, 4, 5, etc. And the continuous, right? Theoretically, you can think of is 1.1, 1.2, etc. Right? But obviously, the common example for the continuous will be age, right? But obviously there are discussions about you only record the integer part of the age, right? But it's just commonly when people do the analysis, they always treat age as continuous because obviously continuous is the most easiest data type to take analysis, right? You don't need to take extra care about, okay, should we keep this integer, how to keep this integer, right? 1, 2, 3, because if they don't, or A, B, C, right? If they don't carry any orders. Okay, so later, right, when we do the R session, you can actually load this data set for both case 1 and case 2 in R and take a look at how the data looks like, right? Under when the data was collected from some clinical study. But here, let's just see. So we for this study, for example, from case 1, right, it actually contains this set of features, so which means we actually take a measurement, right, on the patient on those different attributes. Okay, so first of all, if you look at this arm, right, so which means there were 3 different treatment arms, A, B, and C. So can you tell me which type of this data this arm belongs to?
Categorical?
Yes, within categorical, which one? So here, you see there's a binary, there's a nominal, there's ordinal.
Nominal?
Yes, nominal, because ABC doesn't carry any like orderings, right? And how about age? Which type of data is age? Continuous, yes. And how about sex? Yes, binary. How about race? Yes, categorical, nominal. Let's see what else. Okay, how about this one?
Ordinal?
Yes, continuous. Well, obviously, right, this name is very misleading, right? But if you look at this, somehow you can guess it's continuous, right? Because it has a minimal, it has a maximum, it's a median. So like, well, obviously, I didn't tell how to do the summary on the continuous, but this is how I continuous. Okay, then maybe you can all understand this CD4, right? So what's the type of CD4?
Continuous.
Yes, continuous. Okay, how about this? The weight, right? Yes, ordinal, right? Because there's sort of like the orderings, right, between the categories. Okay, so let's just see the very the most easiest one to summarize is the numerical values, right? If you have, for example, age, right? Okay, so before I show you the slides, right? Suppose you have a measurement of bunch of age, right? How are you going to summarize? So for example, if you clinical study, you involve 1,000 people, so you have 1,000 ages for each people, right? But obviously it's hard for you just to read each of the single numbers yourself, right? Even if you can read it, you probably have no idea after reading this, what this really tells you, right? So can you think about some way to summarize this age information?
Range and then plus or minus standard deviation.
Okay, so have you heard of standard deviation? Yes, right, you all do, right? What does standard deviation do? What standard deviation try to give you the information, try to make?
Spread of the data.
The larger the value, meaning? Yeah, they are more different, right? Heterogeneous with respect to the mean, right? The smaller, in the extreme case, right? If everyone is of age 50, then there's no variability, right? We have identical the people having identical age. Okay, and we also, first of all, right? You mentioned about mean plus minus standard deviation, right? 3 times standard deviation. So first of all, we want to obtain the mean, which measures the center tendency, right? What's like on average, right? The age from this sample. And there are like at least right 2 different ways to measure mean, median. And can you think of another way to measure the central tendency? Yes, mode, right? So the mode. And the measure of spread is variance standard deviation. What's the relationship between standard deviation and variance?
Variance is STD squared.
Yes, squared, right? So basically, the standard deviation and the variance give you the same information, right? You just need to do some operation yourself. And then the IQR, I'm going to talk about later, which provides the interval, right? Okay, so here in this, I guess, at least in this part, the sample size people typically use small n to denote. So, for example, if you have a sample size 1,000 people, then you would say small n equals to 1,000. So people know this is your sample size. And the realization of the data value in a sample will be typically denoted by a lowercase letters. For example, y1, y2 to yn, right? You have to specify what this y indicate, right? So suppose I would say, I am going to use y to indicate the age, right? So whenever you see y1, that means the age for the first sampling unit, right, among your 1,000 people. So here, then n equals to 5, meaning that I only have a sample of size 5, right? 5 measurement on the age, for example. And so here, the y will be the CD4, right? And then y1 meaning that if I go back to my age, right, that means the age for the first people will be maybe 19, right, something like that. So this is tells you mathematically you are going to write the notations like this. And obviously, right, even though we sort of like people commonly use this small n, right, to denote sample size, but whenever you want to introduce a new notation, you still have to tell people what this small n represents, right? And the order statistics, why the order statistics is important? Because sometimes you want to sort the data, right, from the smallest to the maximum, right? Because you want to see the extreme value, right, of this sample. What's the smallest people in your, the youngest people in your sample? What's the oldest people in your sample, right? And also, right, those order statistics can also, when you saw the data, right, can also tells you sometimes whether there's any measurement errors, right? For example, if you are recording the age, you probably don't want to see the age being negative values, right? Or maybe over 150, something like that, right? So immediately you will see maybe there's a measurement error, right? So sometimes people use this to check outliers and also to check whether there's any measurement errors here. And so to differentiate between, the natural, like 1, meaning the first recording, right, the recording for the first people, and 2, the recording for the second people. So they use this parenthesis to indicate this is I smallest sample. So for example, y1, I mean adding this parenthesis, meaning that which is the first smallest, which is the smallest, right, the minimum value of this sample. And then because we only have sample n equals to 5, so y5 within this parenthesis, meaning will be the largest, right, the maximum value in this sample. And you see that from this, right, we actually naturally, and before, right, if you see this sample, it's not ordered, right, because 37 is the smallest and 87 is the second smallest, but they are not ordered according to naturally, right, according to either forward or backwards. But here you see, after adding the parentheses, it naturally tells you, okay, y1 actually representing the smallest. So here, y is not corresponding to the sample unit, right? It's not corresponding to the first people while you labeled, right, in the sample. It's just tell you the smallest value in the sample that you collected, which is among these 5 people. And then this y5 parenthesis, it just tell you the maximum. It didn't tell you how this maximum corresponding to which people, right, in your sample. Okay. So after we learn about order statistics, through the using of the order statistics, it helps us to obtain the median, because the median is the center, right? For example, in this case, 5 is odd number. So the center, which is the middle number, is the median, right? That's the one way to summarize the central tendency. But you might ask, right, what if I have an even number? So the even number, right, because, right, you don't have like single number which is in the middle, then you are just take the average, right, of the two middle numbers after you order everything from smallest to largest, right? So for example, here n equals to 4, then the order statistic will be the two middle number, 87 and plus 194 divided by 2, which is the average between these two middle numbers. And what's the average? What's the mean? Mean is just you are going to adding up, right? So sorry, I think I forgot to mention about the mean. Mean is to actually you are adding up all the samples, right? For example, here you have 5 samples. You are just adding up y1 to y2 to yn. So in our case, yn equals to y4, right? And divided by the sample size. So this is one way to say what's the average, right? The average number within this sample. But the median is that you have to do extra steps. You have to first of all sort these samples, right, from smallest to the largest, and identify the middle number as your median, right? Okay, so now after we have learned the ways to calculate the mean and the median, can you tell me what's the advantage of mean as well as what's the advantage of median? Or like in which scenario you would prefer to use mean, and in which scenario you would prefer to use median, etc. Or at least what's the difference between mean and median, right? If there's no difference, I mean, there obviously has to difference, right? Otherwise, why do we want to invent two different ways, right, to look at the central tendency?
So median is less sensitive to outliers. So the example that I always see is in Chesterfield, the average salary of geography graduates, the median is extremely high, but that's only because Michael Jordan is one of them. So the median is a much more representative number.
Yes, that's a good example, right? So here, right, I think follow what she said, right? So here, let's just say we have first of all, in order to calculate median, we have to order these numbers, right? So for example, if instead of 37, I increase my 37 to like 180 in this case, right? Would that affect my median? No, right? Because 180 meaning that this will be the smallest, and 180 will be the second smallest, right? But the median is still 194, right? The median is still there. So that's why I think that's what she's trying to say, right? Even though if I have outlier, so I mean outlier in terms of, or if I mistakenly, because this is a 385, right? If I mistakenly write a 1 in front, which is being 1,000, right? The median still here is robust, right? Whether I have a very heavy till extremely outlier, extremely rich people, right? The median is not actually getting affected, right? But obviously, if you go back to the formula, where's the formula? Here, it doesn't matter which one you change, right? As long as you change one, at least the one values here, it will affect all the calculation of the mean, right? So here again, the previous example, if I accidentally write a 1 here, so before it's about 300 or 400, now I become 1,400, right? So obviously the mean will get much inflated by just a single numerical increase, right? The number increase. So that's why the median is more robust to the outlier. But obviously, right, you would say if I mistakenly, change the middle number, obviously the median will get impacted, right? But in both ways, both mean and the median will get impacted, right? Okay. Then in this case, why do we need to invent this mean, the average?
Represent people.
What?
It's really useful for like statistical calculations and whatnot.
Yes, and a lot of theories was like sort of like designed with respect to the mean, because the mean, as you see that the operation is much simpler, right? And the median is sort of like the operation is a little bit discrete, right? You have to do the count and find the middle, right? So some of the theories, right, it's harder to prove the properties for the median, but it's easier to use mean to do the follow-up statistical analysis. Okay. Well, this is the choosing the measure of central locations, right? So, and as we mentioned that how to, in which case we choose mean, in which case we choose median, right? It really depends, right? So if you look at, for example, the distribution of the data, if they are all symmetric, right? What does that mean? Meaning that mean and median will be as close as possible, right? So it doesn't matter if you choose mean or median, they will give similar information. But on the other hand, if your distribution is really heavy-tailed, right? So the mean will be heavily influenced towards the heavy tail, right? So how do we say this distribution? I know it's heavy tail, right? But how to properly say? Yes, right. But it's skewed towards which direction? I mean, there are like scale towards both directions, and this is a scale toward one direction. You see, this is a scale towards another direction.
I can never remember visually.
Yeah, so first of all, it's skewed, right? It's heavy tilt towards, you could say like, this is towards the right, right? Because this is on your right hand. This is a heavy tilt towards the left, right? Or the lower value, right? Yeah. Okay, so in this case, let's say, in this case, right, suppose let's look at this first one. Would we expect, so what's the, how, if we compare mean and the median, which one is larger, which one is smaller? Mean is larger. Yes, because there are lots of like larger numbers as it towards the right? So the mean will be put towards the tail area, but the median will be sort of like robust, right? Okay, so this is a central locations, right? And then we talk about measuring the spread, right? Even though we have the center, but then they can be, the sample can be very different from the center or very close to the center, right? Which is the spread of the sample. And the one way to look at the sample variance, right? So basically, if you look at this formula, meaning that we are going to use each individual observation minus, which means we are looking at the difference, right, or the distance between each observed value versus its central tendency, right, which means with respect to its mean. And we are taking the square because we are only interested in how far away, right, this sample with respect to the mean. We are not interested in whether it's smaller or larger, right, just the distance, right, how different they are. So that's why we are taking the square and we sum them up and divide it by n minus 1. So this is a formula for the variance, right, s squared, denoted by, we use s squared to denote it by the variance, right? And the standard deviation, meaning that we just need to take the square root of this s squared. So that's just a standard deviation. And there's another way to quantify the spread, which is the IQR interquartile range. Have you heard of this IQR before? Yes, right, because when you generate this box plot, so here, the box plot, right, this is generated through the calculation of this IQR. So basically, the IQR is defined between the distance between the 25th and the 75th percentile of the data, right? So it gives you a range of, okay, how, what's the distance, right, of the variability of this sample looks like. Obviously, the larger this IQR, meaning the more heterogeneity of the data are with respect to the center. Measure of the spread. So again, right, if you look at the formula, this formula looks similar to the formula of the mean, right? We're actually taking into account of all the data, right, to calculate for either variance or standard deviation. So that means if there's any entry error or any extreme values, right, this will make this inflate this S square, right, differently or decrease or increase largely. So similarly to the mean, these variance or standard deviations are very sensitive to the outliers. But if we look at this formula for this IQR, it just relies on the use of order statistics, right? So it's sort of like less sensitive to those extremely small, extremely large values, right? Because just to look at difference between the 25th to 75th percentile. Okay, I will stop here and let's take maybe 15 minutes break. So we will restart at 10:45. Okay, sounds good. Okay, so now let's start the second part. Okay, so I will skip this exercise for now because I want to save time at the end so we can, start with manipulating of R and import the data and you do the analysis yourself. You try to run the code and see what happens. Okay, so last part is graphical summaries, right? So before we talk about how to numerical, right, using number to summarize the data. And the most important thing, right, is to visualize the data, right? So it give you a better sense, right, of what the data looks like with respect to the sample you are collecting. Okay, so obviously different graphical summaries or different visualizations will really depend on the data types, right? And so first of all, the categorical data, because the categorical data is sort of like category, right? So once you have the categorical data, the natural thing that people want to do is to count, right? Count how many data points falling into each category, right? For example, if you collect data about the gender, you want to see how many people are female and how many people are male, right? So the count or the frequency, right? For example, in the entire sample, is it like more than 50% of people are male and less the female, right, etc. So here, for example, this is the mode of, I guess, treatment, right, or the something. So it's categorical. So what people do is that I either take the count or take the relative frequency, meaning that I use the count divided by the sample size, right? So they generate this sort of like bar graph, right? I mean, the number of bars, so here we have 1, 2, 3, 4, 5, 6, 7 bars, meaning that because for this mode of transmission, for this mode of transmission, we have these 7 levels, right? Which is 7 levels for this variable. And then the number 22377, 103, etc. They are the counts. That is tells you, okay, how many people fall into this mode, how many people fall in this mode, etc. And intuitively, right, what you can get from this bar chart.
Two main modes.
Okay, you got too many bars, right? So what else you can get? So at least, right, by counting the bars, right, you know how many modes are there, right, at least, right? And what else you can gather from this plot? The information, the distribution. What distribution? How to describe the distribution, I guess. What? Yeah, scaled, right? So it's not, first of all, it's not like uniformly distributed, right? So one has, or at least these two mode, the type of transmission has the majority of the people, right? And then there are the other type of transmission has like much fewer number of people. And so this is telling you by count, right? 2, 2, 3, 7, 7, etc. And this tells you the frequency, the percentage, right? Meaning that this is the same, right? If you look at the distribution, they are the same. The only changes is just a number, right? This is derived from the count by using 2 divided by the total sample size, right? So they're equivalent. It just gives you different way to summarize the height of this bar, right? So depending on your preference, maybe some people feels like, so this is not a count, right, which is a percentage. So people feel like in terms of percent or the frequency, right, it's more intuitive, right, because it tells you, okay, what's the percentage, and this suppose you have two studies, right? It's sort of like directly comparable across percentage versus count, right? Because count is one study has fewer number of people, the other has larger, right? So the count, they are not directly comparable. Okay, so this is the bar plot. The other is the histogram. So the histogram, as you can see here, for example, this histogram, it's sort of like similar to the bar plot. It's just the bar plot is designed specifically for the categorical data because those bars are actually determined by the levels, right? But the histogram is the similar the graphical visualization to the bar plot, but specifically for the quantitative data. So, for example, if you have a continuous data, right, you want to see the distribution, for example, of the age, you could sort of like split this continuous number into multiple categories, right? And then you can sort of like count the frequency of people falling into this category, or this being, the other being, etc. And then it shows you roughly the distribution of this continuous data, right? And how do you describe from this histogram, what information can you gather by looking at this histogram? So basically, right, the histogram tells you those are the different beings, right? So this, for example, HIV RNA, this is the variables that you are interested to look, right? And then this is a unit, right, 2, 3, 4, 5, associated with HIV RNA, right, this variable. And the y-axis, the vertical axis, are the frequency. That is, what's the frequency of the people falling into this being, right? Well, this being is people having this HIV RNA much greater than 5, right? Which is the top, right? The most, like having the highest HIV RNA reading, right? And then this is the second highest, etc., right? So from this histogram, what information you can gather to sort of like describe this HIV RNA variable for this sample?
The mode is the highest value?
The mode is the highest value. You are saying this one, right? Yes, okay.
It's also less skewed, so we see a lot of people with a lot of HIV RNA.
Very small, right? So for example, we could say, while the majority of people having sort of like average, right, greater than 3.5 this value, right? But we see a sort of like outliers, right? They have extremely, right, close to zero, this HIV RNA values. And this is sort of like, well, another way, also another thing we can say is that it's sort of like in the sense of it's unimodal, right? The mode is sort of like at the tail, right? And also, right, another, we could also make this histogram more meaningful in the sense that if, right, besides we have one continuous variable, HIV RNA, we can also have another variable, right, which is, for example, here, binary. So this is just one example, right? What if we have a categorical, we can generate a multiple histogram, right, for each level of this categorical value. So here, for example, we have sex, which is a binary, female, male. Then you can actually make histogram within each gender level, right? So what's the advantage of doing that? To generate this multiple histogram for the same variable, like the continuous variable, but based on different way to stratify your sample, right? What's the advantage of that?
Compare differences.
Yes, so you can compare, right, whether they follow the same distribution, meaning that the gender is not a factor, right, to influence this HIV RNA, right, or gender is really a confounding factor to that, right. But remember, when you plot this, like two histograms, right, you have to make sure that the y-axis, which is the vertical axis, they actually share the same unit, right, the scale. Otherwise, it's really misleading, right? If you plot them to different scale, then it will give you misleading results. Okay, so from this, right, so now since the histograms are already generated between female and the male, what do you think of these two histograms? Are they the same? Are they different? If different, how are they different?
They're different in that females seem to carry or harbor more HIV RNA.
You are saying about this one, right? Yes. The frequency, right? The male is sort of like a higher percentage of female having extremely large, right, HIV RNA reading versus the corresponding the male people. And what else?
Also looks like you have a lot more males in your samples than females.
I have a lot of male in my. Sorry, the other way around. Yes, that's a good observation. Oh, what else? So if we sort of look at the one tail, right, of this distribution, maybe we can compare the other tail, right? So maybe we could, well, at least for me, right, I am thinking about, you know, for the female, it has more like people having extremely low HIV RNA reading versus male, right? The outlier towards the left is relatively, right, much more frequent than the male per se, right? Well, obviously, right, this is just a visualization. Different people, right? For example, this example, the histogram, they are sort of like there may be no clear, like maybe distinct difference between this, right? So different people may have different perspective, right? That's a common way to describe or to understand this visualization. But the idea is that the visualization, you have to think about using the visualization to gather, I guess, the major information, right? But not too much of a detail, because the details will later we are going to use statistics, right, to officially or to formally talk about whether there's any significant difference between the gender, right, male and the female. But here, just give you some ideas, right, in terms of how this data looks like, give you some summary information. And another is the box plots, right, for the quantitative. We mentioned about IQR, right, previously. Where's IQR? Which is the way to measure the spread, right? How, I guess, how much variability within this data set. So the IQR is determined by the 25th and the 75th percentile, right? The small part and the larger part of the data, and also the median in between. So here, based on this IQR, we can generate box plots, right? Which is a graphical display of the median, 25th and the 75th percentile of the data. And sometimes, so you will see those dots. Those dots are sort of like determined by the outlier, right, which falls outside this box. Well, how to determine this outlier is represented by the observations within 1.5 times this IQR, the interval of the data. So they use these dots, right, to represent those sort of like suspicious outliers, because it's going to be extremely far away from the center. So here, from this box plot, right, what can we see from this box plot? So first of all, we have to understand, right, what's this line representing? This is the median, right, the center. And what's this, the width of this box? Yes. And so the most meaningful way to compare the box is you have like lots of box, right? So you can sort of like compare, okay, do they have obvious difference among the mean, right? So what do you think of this? Do they have difference in terms of the median, I guess? No, right? So this is like, they don't have like a visually significant difference among the median. How about the spread and etc.? Are they similar, or are they extremely different? Yeah, so this is how I visually, right? So here it's like between these three different arms, right? A, B, C. What do we see about LDL? They don't really differ in terms of the box plot, right? Roughly, those are summary statistics. they actually perform similarly. And how about this? If you look at this box plot, well, obviously the center is here, and we see lots of dots here. What does that indicate?
Where?
Yes, so basically the distribution is sort of like heavy tailed, right, towards the left. And here it's sort of like we are performing the comparison by sex. So basically we have actually two box plots, right? So from the comparison, we could say, well, again, right, so here is, you see the sex is actually indicated by the 0, 1 instead of female, male, right? But so remember, whenever you want to use the number 0, 1 to denote this a binary variable, you probably, I mean, the same thing for the other categories, right? You have to sort of like indicate what this 1 represents, right? So here, right, I have to guess whether the 1 is female or male, right? Okay, but here we could say the mean, right? If you look at this 0 to 1, the median is slightly lower for the for 0 than the 1, right? And how about there? And also in terms of distribution, both of them are heavy-tailed, right, towards the left. Also, here is the caution. So the caution says while box plots are helpful, they are not. Let me just make it large. They are not sufficient graphical summary of data. They are limited by what characteristics can be displayed. So here, if you look at this box plot, right, what do you think of this box plot? They are sort of like perfect, right? They are assuming, or by looking at this, we will assume this data is symmetric, right? Centering around 2, and then the tails, they don't have obviously heavy tails, right, towards either side. But then if you look at the histogram of the data which was used to generate this box plot, if you look at this histogram, this is actually telling us this distribution is by model, right? So that means what this tells you is that sometimes the median is also not either the median or the mean, right? They are not sufficient summary statistic about the center, right, of the location. Because if, for example, we are using the mean and the median, assuming that the distribution is sort of like unimodal distributed, right? If you have a multi-model, for example, in this case, bi-model distribution, what do you think, how we can summarize the central tendency of the data? Yes. So first of all, it's very hard in statistics. People are still like thinking about a better way to summarize the central tendency, right? But here, if high level, right, if we look at distribution, we see there were 2 modes. Then basically we could use a mode to describe, right? At least there were 2 modes. So one is near 0, one is near 5, right? And also, right, sometimes people are still using either mean or median to describe the central tendency. It's really, you know, for like follow-up statistical analysis, right? They're assuming that sort of like the mean is really, because someone argues that the mean is really sort of in the middle, right? So, but again, this is a more difficult scenario. So there were actually more like a sophisticated method that were developed to handle this. What if you have a multimodal distribution? The mean may not be a good summary statistic to summarize the center, right? But that's sort of like beyond the scope of this workshop. So, but just to let you know that the data can be, you know, very of different ways, and we have to pay attention, right? So the visualization is really important. The first step, right, towards you are going to perform more sophisticated statistical analysis. And also, the last part is that there's one variant of the box plot, which is called a violin plot. So I think that this violin plot is more commonly used in biomedical research, right? People like to, you know, looking at these nicer shapes, right? So that it provides, you know, more information than just using the box plot. And so I guess another common way to look at the data, right, especially if we have paired data, right? For example, for each individual, besides I measure their age, I will also measure their height, right? Then that is paired within each people or the sample unit. There were two quantitative variables. Then the most, I guess, intuitive way to generate this scatter plot, right? One axis represents each variable. So here the x-axis is age and the y-axis is the LDL. And the dots are the sampling unit, right, within each sample. So how many dots are there equals to the sample size, right? Okay, so what people use this scatter plot is trying to identify whether there's any pattern, right, between this x-axis and the y-axis variables. So here, if you look at this scatter plot, what can you say about the relationship between age and LDL, right?
No. Trend.
Yeah, for me, I feel like, well, they just scatter around, right? There's no obvious, at least, right, visually obvious trend between this age and LDL. But if there's no trend, can we say, well, age and LDL are independent? No, right? So the trend is sort of different from independent. I believe that you are going to learn the independence concept later. But here, just say, well, there's no obvious trend, meaning that, so what we think, I mean, when you talk about trend, what trend are you thinking of? What is your definition of trend?
Linear regression.
A linear, sort of a linear trend you are thinking about, right? Or some functions, right? Even it's not linear, maybe they are like curves like going up and going down, right? But here it's sort of like really hard to tell. Well, you could say, right, roughly there's a linear trend, but it's just it's too noisy on this direction. Right? It's really hard to tell. Yeah, basically. And how about this? So this is another scatter plot representing the relationship between weight on the x-axis and this log transformed HIV RNA. What do you think of this scatter plot? First of all, besides the trend, right, I would say there were some few outliers, right? For example, here at the y-axis, right, that's HIV RA, right, they have a few outliers here. And for the weight, there were definitely, at least there were like one outlier, right, which is on the larger side, right? So besides the scatter plot tells you the relationship, but sometimes it can also tell you the outliers, right? In which direction, whether there are outliers, right? In both cases, or outliers in one variable and outliers in another variable, right? And what else? And besides the relationship, right, we can identify some patterns, right, in the data. For example, I mean, obviously, right, you can, the observation is that there may seem like two clusters of this data, right? One is like people having extremely low weight, right? And people having like moderate weight here, right? So two clusters, and the relationship between like within each cluster of the weight versus HIV RNA may be a little bit different, right? So this is just observation, right? I'm trying to say that by the scatter plot, you can actually discover more than just whether there's a linear trend or like curvature, etc. You can identify outliers, you can identify patterns, right? And also you can make this scatter plot more meaningful, right? Because, for example, if you have another variable, for example, outcome, right? If the outcome is binary in the sense that infected or not infected, right? Then you can also color code these dots, right? So one color, for example, red color indicating HIV infected, right? Black color indicating non-infected, right? You could see how the color distributed on this scatter plot. Also here, right? So here is the color, right? You can, so the color is labeled by the sex, right? You could see, okay, how the sex distributed among the scatter plots. And you could do like simple regression, which we are not going to talk about this in details in the, in today's workshop, but there's you can fit a regression line, right? And you can also fit a separate regression line, then tells you that maybe, the relationship between weight and HIV RNA can be different, right, across this gender. But obviously, right, whether the difference, right, the slope of these two lines are significant or statistically meaningfully significant, right, you have to perform hypothesis testing. Okay, so the last part of this graphical summary is that what if, right, you are collecting more than two continuous variables, right? So you can have this lots of like pairwise scatter plots, right? So the diagonal, for example, here you have four variables: LDL, age, HIV RNA, and CD4. And you can generate this pairwise sequence of these pairwise scatter plots. So how to read this, right? So if you look at the first one tells you that this x-axis corresponding to the age and the y-axis corresponding to the LDL. And then your job is to see whether, so what I see without looking at these blue lines, I would see there's a slightly upward trend, right, between age and LDL. And maybe slightly here, at least this is obvious outliers, right? On this age side, not LDL side right here. And by looking at this plot, right, you could say this particular data point can be influential, right? Because visually, I would say the upward trend, but then it's going to go down because of this particular data point, right? It's influencing the model we are going to fit, right? And how about this box next to this? So how to understand what this x-axis representing is that you are going down towards this middle, right, this diagonal. This tells you that this x-axis is represented by HIV RNA. And again, this y-axis is corresponding to this LDL. So now this scatter plot tells you the relationship between HIV RNA and this LDL. And similarly, this one tells you the CD4 versus this LDL. Right, so this is how you are going to understand or look at this pairwise, this sequence of pairwise scatter plots if you want to look at the relationship among more than two continuous variables at the same time. Okay, so this is actually everything that I want to talk about today. And for the rest of the time, I want to start with this R. So from your introduction, I don't hear many of you have learned R before, right? Have you ever worked with R before?
Yes.
Yes, okay, you have, right? Okay, that's good. So if you can go to this, I think this website is in Kelly's email, right? So if you can go to this DCC on demand, can you? And you click on this CHSRI R Studio workshop, and you scroll down, so it's already tells you this is R25 workshop, and you click on this launch, and it says it's queued, so you just need to wait a few minutes. Okay, so now it becomes running. So if it's running, you just click on connect to R Studio server. So if you have any questions, just raise your hand so Richard can help. Or if you, okay, if everyone has already opened that, Okay, so you go to let's see. So you can see this is our code to have this lecture. And then if you go to, do you have this statistics folder, by the way? Do you see, right? You click on the statistics folder, and you click on this more, and you set this as a working directory. No? No.
Yeah, they have a pool. You sure? Yeah.
Okay, so Richard will tell you how to get this data folder.
Okay. Hopefully this works. Okay. So if you are in DCC on demand and you're in the project folder, or if you've like you've like made a clone of the repository on DCC. How many people have done that to start with? Okay. And so you're going to just pull with rebase. I believe is it. Hopefully this works very quickly. Cool. And then now everything's in there. Yeah. So it's this down arrow to pull. Okay, I'll come over there. All right.
Thank you. Okay, so everyone got the data folder? Yes? Oh. You are on DCC, right? Yes.
I don't want to make it, yeah. So, do you have a, yeah. And then do you have
the same problem, it's that, yeah. Okay. Okay, so for those like people that you can get the data, right? I just want to say that, do you also have this RMD file open? You get this, right? So probably it's much helpful that you open this RMD file because all the R codes are here. So here, this is how I set my directory, but you don't really need to use that. You just go to, like, in this, right, go to click on statistics, have this page and click on more and set working directory, right? So you are here. And so if you go to this, right, this is helps you to, so this is to help you to read the data from this data folder.
Yeah.
Okay. So if you can just copy and paste. Richard.
Yep.
So if you can open this, right, and then in R you just type case 1. And it will give you, okay, how this data looks like, right? Tells you how this data looks like. one, I think I'm waiting for the other, like to get, be able to have this data. Maybe you can play around with this data a little bit, right? For example, how to get to know the size of data, right? You can have DIM, right? Dimension. So it tells you the rows, that is how many people are here, and what's the column number, right? 31. That is, you are recording 31 features. And if you are interested, right, you can just scroll down to look at this R code, right, to read the case 2, and just do the analysis yourself. At the meantime, just let's wait. Oh, because this is my study for so for you, it's actually like this folder, right? So you just hear it from that. It just helps you, okay, no, you are doing yeah. You can use a neat instead of this higher one. But here I want to emphasize so whenever you get the so this is the way to help you how you can plot data. So here, for example, data is 1 to this R. You can just copy. Yeah, okay. Yeah. On that now? Yeah. So basically, for those people who are new to this R markdown, so everything within this R chunk denoted by this R are the R code. So you can scroll down to see the R code and try to copy and paste, right, just to see whether you get an error. So so how to read the data is from this R chunk, right? So read.csv helps you to load the data from this data folder because they are all CSV files. You're already here. You're already interested in this project and then feel free to clone it again. So besides like this problem, if you have any questions in terms of our errors, you can ask. Do you have any questions? Did you get anything? Okay. Okay. So you are good? Oh, okay, so what is that? Oh, yeah.
Yeah, you can. That's something to do with, you know, how it works. So once you run it, it's not
Yeah, so if you had
Let you go.
Yeah, so first of all, so we can know how to manipulate it. Okay, so you got the data. Okay, that's it. So everyone got the data, right? So you use this read.csv file so you can read the data. So the data is here, and we can summarize the data. First of all, we can use this DIM. And by the way, if you have any questions, right, in terms of what this function is doing, you can always type question mark and followed by this function. So here, this just tells you what this DIM doing. It tells you, gives you the dimension of this data, right? The dimension, because this is a matrix. the dimension of the row is about 4,000 and the columns is 31, right? Basically tells you, first of all, how big is your data. And then you can also look at this column names, right, of your data. So what are the features, right, we are measuring for this data, right? And from this, right, you can have a clear, basic understanding of, okay, what are we recording, right, in this data set. I believe, can we have a summary of this? So the summary, right, the summary function gives you what you have seen before, right, the lecture notes. Gives you the basic summary of each of these variables, meaning that what's the mean, what's the maximum, what's the this IQR, right? If they are numerical, and if it's not, then they give you the counts, right?
Would you mind doing that?
Here, oh yes, yeah. So basically, right, this is doing the summary, right? If you just have the summary followed by the data, then this gives you this, right? And what else is that now you want to, okay, generate the plots, right? How to generate the plots is, okay, so first of all, given this, for example, how do I say if I particularly want to look at this HIV RNA, right? So let's say case 1. So if you type $sign after, directly after this variable, right, containing your data, it tells you, okay, how many columns, right? What are the columns associated with this particular object? So you can use your keyboard to say, well, what if I want to just look at this HIV RNA, right? You click on this and you type enter. So this gives you everything, right? All the recordings for this about 4,000 people with this HIV RNA reading, right? And now you have this, right? But obviously, this is too many numbers for us. How should we do? Because this HIV RNA is continuous variables, right? Obviously, they have NA values. But we could say, well, hist, right, which is a histogram of case 1, and again, $sign, right? HIV RNA, right? So it tells you, okay, this is a histogram you are actually seeing, right? Why this happens? Because this data is too much heavy-tailed, right? So that from this direct using this histogram, you don't really see anything, right? Because you see most of cases they are 40, but then they have extremely large values, right? So from histogram, you don't see anything. What should we do if we have variables like this? What? Change scale, right? How to do that? Use some.
Change the bin of the histogram to like spread it out more.
Okay, this is one way, right? Instead of change data, let's change visualization, right? Okay, so let's see how to change the bin, right? So let's use a question mark and followed by this function hist, right? The breaks, right? How to change it? Where's the breaks, right? Can I say 10 or something? Okay, say, so here use breaks, right? Breaks equals 12, and you can change that, right? Let's say histogram of this, and breaks equals to 100. So what happened? Well, obviously we have this a lot of things, right? But still, the problem you see that it's really because of this is heavy-tailed, right? Much heavy-tailed. So in this case, we tried to change how we generate this histogram, but it's always not giving us a satisfactory result. So this time we have to change our data, right? We have to change the scale, that is, do some transformation. So whenever you have this heavy-tailed, right, and non-negative values, people typically use log transformation, right, to bring an extremely large number towards the smaller side. So can you do a log, for example, log case 1 and HIV, right? Okay, so you see that in R, right, if you already have this missing value And if you apply those transformations, this missing value will still remain missing, right? So you don't need to worry about the missing, right?
Is that missing or zero value?
Oh, it's missing, I think.
Okay.
Yeah. It is, yes.
Oh, yeah.
Right, yeah. Yes. Okay, so once you have this log, right, then you can have a new variable name for this HIV, right? For example, I could say log HIV RNA, right, to say, well, this is actually log-skewed HIV RNA, right? So you can assign a new name for this. And once you do that, you can just directly say hist log HIV RNA, right? So this gives you the much informative histogram, right? Okay. Okay, so this is the histogram, how you generate this histogram. And you can also do the box plot and the log HIV RNA, right? So this gives you the box plot. Obviously, you see that this box plot, you can also zoom it, right? The box plot actually suggesting that even I do log transformation, it's still much heavy-tailed, right? But it's much better than if I don't do the log transformation. Good. Yeah, okay, that's good. So let's just see, right? So if you look at this case one, you have this sex, right? You have a female, male. And then you can look at the structure, STR structure of this, for example, case one sex, right? It tells you, you see the R actually store this sex information as a factor, which is like categorical, right? It's not a continuous 0, 1. It's already treated as a categorical variable. And how you can generate, multiple box plots, for example, per male and female. Do you know how to do that? What? You have a class? Oh, it's a workshop. Yes, but it's 12. I mean, oh, we have a fan.
Also, this will end it. Oh, we will need to set up
but here we still have 30 minutes. Maybe I can add it like maybe 10 minutes or. Yeah. So this is a really popular room, so you have a lot of scheduling here. But I mean, I will stay here till noon, so maybe I will just disconnect my laptop, right? Like 10 minutes earlier, so you can have any questions, right? We can just Richard and I will stay here so to answer any of the questions. So I asked about how to generate like 2 box plots, right? What? Offensive, right? Oh, you are more advanced. So this is required using the ggplot too, right? Oh, everyone's familiar with that? Oh, why do I teach this? We can end early, right? So, okay, so yeah. So is there anyone never used ggplot2 before? No, right? Okay, that's good. So basically, it's a more popular R package, right, to generate more like a beautiful, prettier plots than this basic version. But here, right, before, right, but I guess the ggplot2 requires slightly more effort, right, than you just having a data and you just want to quickly see how it looks like, right? Because here you can just directly say hist or box plot using the default function. I think. If you can say box plot, right? And you have case 1, HIV RNA, this, and case 1, so this automatically gives you, right? So instead of you are thinking about, okay, the facet and something like more fancy, we just give you a quicker, right? Much quicker visualization before you determine, okay, which are the plot you want to make it prettier or fancier, right? Yeah. Again, there are like advantages using this default function to generate this plot, right? Okay. And I believe that you also know how to do the subsetting, right? If you want to select certain part, for example, if you want to select the sample only contains male, right? You know how to do that, right? And how to do female. And this is if you go back to the lecture notes, right? And you can, show all the code, right? So it will tell you, it gives you some examples, right? How to generate this pairwise scatter plot. In R, the default function is just the pairs, and then you could tell them, tell the R, right, which variables you want to use to create this pairwise scatter plot. And similarly, right, so this, if you look at this, a scatter plot tells you, okay, well, this is using a ggplot, right? It gives you a nicer visualization. So if you are not familiar, I think you could, after you load this data, you could, play around with this R code to get a sense of how to generate this data if you are not familiar with that. And if you go to this data type and the summary statistics, right? So it tells you, okay, how to do a summary, right? Basically use a summary function and it gives you everything. And you also know how to get mean and median in R, right? Right, just the mean and yes. Okay, since everyone's expert in R, so maybe I'm not really sure what I should tell you. Maybe I think, right, for the best of time, maybe you if you want, right, you could look at this R code from the lecture notes, right? Just try to reproduce the plot, right? And maybe it happens that you have some errors, right? And you don't know how to fix it, right? Then we could, or if you have any questions, right, related with what we have taught today, right, you can also ask either Richard or me, right, for clarification or something. Or if you have any other questions, right, or any questions, feel free to ask. Okay.